Hello, and welcome to today's webinar presented by Líbilo software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is CSA S16, 2019 Steel Design in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Alex Bacon will be your moderator, answering any questions you may have. He's a technical support engineer, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. I always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So to cover the content that we'll be going through over the next hour today, we'll first begin in our main finite element analysis program, RFEM. And I've taken the liberty today, for the sake of time, to fully model our steel structure as well as load it. So we'll give a quick overview of that directly within the program. Then I want to move on to the new Annex O2 stability requirements that were recently added to the CSA S16 2019 standard. So this will have a lot of impact with our analysis that we'll be going through step by step in quite a bit of detail and applying these requirements directly within RFEM. Finally, we'll be ready to run an analysis. And from here, we'll take a look at our results. And the results from the analysis might include information such as the deformations. We'll also take a look at the member internal forces. After this, we're going to utilize the add-on module RF-STEEL CSA. And this add-on module is integrated within RFEM that allows us to perform the steel member design according to this recently released standard, the CSA S16 2019. Finally, we'll take a look at our results from the steel member design within this add-on module. So we'll immediately begin with our example today in RFEM. So this is our main FEA program. As I mentioned, you can see that I have taken the liberty to model our steel structure here. Over on the left, we have our project navigator. So all of this input data, such as our cross sections, our materials, can all be accessed within this project navigator. We'll also have the ability, once the calculation is run, to view our results within the project navigator as well. Down at the bottom, we also have our table input. So if perhaps we don't want to model our structure graphically, we can utilize the tables down at the bottom. Our results will also be available to us in table format. So to quickly give a brief overview of what our structure exactly consists of here, you'll notice that we have a couple of moment frames in the interior here that are a little bit bigger than what we're seeing at the exterior. So taking a look at these members in particular, you'll notice they are W310 by 79, material steel 350W. The member type is just a typical beam member. So this would just be any type of beam or a column. Everything for these frames are fully fixed. So the member hinge is set to none, which just means that all forces will be transferred where they're connecting to other members. If we take a look at the members, the exterior here on either the left or the right side, similar concept. We have moment frames here, but definitely a much smaller member, a W130 by 24 steel 350W. Member type is set to beam, fully fixed. For our interior columns, though, you'll notice that we have a special symbol up here at the top, and all that I've done for these W130 by 24 is to apply a moment release at the top of the member. So that graphic is shown here within RFEM to represent this moment end release that I've set directly within this dialog box. We also have these purlin members. So these are framing in between our frames, and they are set actually to the member type truss. So the member type truss just means that essentially we're going to apply that moment release internally for the calculation. So it's grayed out down here at the bottom because the program will automatically apply that for us. These are just typical HSS 127 by 4.8 steel 350W sections. Now, in a similar sense, we also have our lateral bracing here. If I double click on this member, these are single angles, L51 by 51 by 3.2, steel 300W. The member type here, though, is set to tension only. So this member can only take axial tension forces. If it has any compression, it will automatically be removed from the iteration. Now, RFEM will allow this member to be reactivated, though, if a tension force is reintroduced to it. And once again, we're going to apply those moment releases at both ends as well as shear releases. So it's only transferring those axial forces and tension. Now you'll also see that the main rafters here are split into individual segments, and this is fine for the analysis purposes, but later on when we get into design, I'd actually like to consider these as one continuous member. So what I've done in the model is to hold down my control key to select all 4 of these segments. I can right click to create what's called a set of members. And all that this set of members does is it will group together these individual segments here for design purposes. It does not affect the analysis whatsoever. And this will make a little bit more sense once we get into the add-on module. But you can see the symbol here, a faint dotted line grouped around these 4 individual members. Down at the bottom, you'll also notice here that we just have typical nodal supports applied. If I take a look at the detail settings here, we have 6 degrees of freedom. I just went ahead and applied a support within translation directions, X, Y, and Z. And then I've also added a restraint for rotation about the column's own axis, so it's not free to rotate in torsion. So that really summarizes a brief introduction just to the steel members, the materials used, the types for this example today. So what we'd like to get into next is just a brief introduction to the loading. So I'm going to turn on my load cases and combinations dialog box. And you'll notice here that I have created 4 load cases. I have my dead load, snow load, wind in the X, and wind in the Y. Now all of these are set to the action category according to the NBC standard, which does affect our load factors for our load combinations. So nothing too complex here. And once we have set up these load cases, we need to actually apply the loads within RFEM. So I go back to my graphical display here and notice that I have dead load selected within my drop-down box here. Now I can turn on my loads graphically that I have already, again, taken the liberty to apply to the structure. Notice I have just a point load at the top of each one of these columns. And I also have a distributed area load. And I created this automatically within the program. Under Tools, Generate Loads, we can create an area load on members via a plane. So within this dialog box, it's really quite simple. I'm just applying a magnitude of negative 0.02 kips per square feet in the global Z direction. And then I select my corner nodes that it's going to apply for this plane back here in RFEM for the roof. Now I took it a step further and I said, okay, well, I'd like this area load to only be applied to my main rafters here. I don't want them to be applied to the smaller purlins. So I can take any one of those purlins, graphically select it here, such as member number 33, and then all purlins that are parallel to member number 33 will automatically be deselected when it comes to this area load. So if we take a look at this generated area load, I have the ability here to right click and display separately, and notice only the rafters are affected here. The magnitude is given to me before I run the calculation just based on the tributary area of each one of these sets of members. Now I also created this snow load in a very similar fashion. This was also a generated area load. Now the difference here is obviously I wanted to change the magnitude slightly to 0.03 kips per square foot, and I applied it in the projected Z direction. Now the difference here between projected versus the global is that we'll take into consideration the angle of this roof for the applied magnitude of this snow load. If we have a very steep angle, we're obviously going to be seeing less snow load than what we'd see on a roof that was completely flat. So when we take a look at this generated area load, we can right click to display separately, and here's our projected snow load on each one of those rafters. So I've also applied a wind in the X direction, pretty simple application here. So according to the global X axis, we have our wind flow from left to right. And over on the left for our pressure face, these are just standard member loads that I've applied to each one of these members. Over on the right-hand side, we kind of have a suction force, again, just with those typical member loads. Wind in the Y, a similar concept here, except for we're going to have wind flow according to the global Y-axis from right to left. We have our pressure face over here on the right with member loads, and then a suction force on the left with those member loads. So now that we have created all of our load cases, the next thing to do is to combine them into load combinations. So when I first created the model, which we can access the General Data tab afterwards by right-clicking on the model name here, you'll notice that I selected the NBC standard to automatically generate my load combinations. And within this dialog box dropdown, we're also seeing the ASCE 7, the IBC, Eurocode, and other international standards. So when I have this option checked here, we'll automatically generate these load combinations according to the standard that's selected. Now I also have the ability to uncheck this option, and then I can just manually create my load combinations instead. So once we have our standard selected, we're going back into our load cases and combinations, and we'll jump to our combinations expressions tab. So the program's telling me it's going to generate those factored load combinations according to the NBC, so our ultimate limit state. If I'm curious to see those, I can click on this little info button here, and I can see directly what the NBC calls for in terms of those factored load combinations. We also have our serviceability or our unfactored load combinations listed here. According to the NBC, we have a few different options for serviceability. And again, we can click on this info button to see exactly how those will be generated. So most importantly is to actually jump to my load combinations tab, and we can see our factored load combinations generated here with the red color, and then our unfactored with green. And this is only considering those load cases that I input under that first tab, so dead snow and wind. Now, it's important to know that under the calculation parameters, by default, we're automatically going to consider a second order analysis for all load combinations. Now, you can change that here, but most standards, which we'll actually get into this in quite a bit more detail in just a minute, do require a second order analysis. RFEM will consider big P delta and little P delta effects when we select this option. And finally, we have a results combination, which is just nothing more than an envelope solution. So we have a results combination for our factored load combinations and a results combination for our unfactored load combinations. This is just going to provide us with the max and min internal forces, deflections, and so on, if we were to view these within the program after the analysis. So now that we have gone over the initial modeling, the initial loading, I want to jump back to the PowerPoint now to begin our discussion here about stability considerations. So if we refer to the CSA standard, and in particular clause 8.4, the code tells us that we must consider structure stability, of course, for the overall design. Now, these stability requirements are elaborated on in clause 8.4.1. So we should consider deformations, big P delta, little P delta. We have geometric imperfections, stiffness reductions, and uncertainty in stiffness and strength. So there are actually a couple different methods of analysis and design for stability, and these are provided in clause 8.4.2. Now the first, which is nothing new, this has existed within the CSA, is this simplified stability analysis method according to 8.4.3. So most of us today that have done design according to the CSA standard should probably be quite familiar with this section. But what has recently been added within the 2019 standard is Annex O, and in particular, Clause O2, which now defines an alternative method for stability consideration effects for an elastic analysis. So we're going to be getting into this quite a bit more today and applying this to our example. But before we do, I do want to cover the simplified stability requirements. And again, most of us should be familiar with this according to clause 8.4.3. And this is the initial method. This only has a couple different requirements listed here. And the first is to consider big P delta effects according to 8.4.3.2. So we should all be pretty familiar with P delta effects, but I've drawn a little diagram down here in the lower right-hand corner just to kind of convey what P delta is. Essentially, we're going to have a vertical member here with an axial or gravity load applied to the top of the member. Now, when we apply an additional lateral load here, we know that the member will, of course, deflect, but that gravity vertical load here is also going to deflect. And it's going to deflect a certain distance delta. And this is obviously going to create some type of moment on the member. So these are the effects that we need to consider and is required again for most standards. Now, there's also P little delta effects, and we can see this diagram shown here. This is a little bit different than big P delta. It's actually going to be the deformation along the member length, these small deformations that occur as the member distorts. So referring back to 8432, the code only addresses big P delta, and we must consider this in one of two ways. The first is a second order analysis. So lucky for us, RFEM automatically applies that second order analysis for load combinations. Now, the other alternative, let's say you have a structural analysis program that does not automatically apply second order effects, or you're doing hand calculations, is you do need to consider this U(2) amplification factor to both axial loads and bending moments. And this is according to 8432B. So again, if you can't meet this requirement of a second order analysis, let's say within your structural analysis program, then you'd probably be taking into consideration P delta effects with this amplification factor. The second requirement from this simplified approach is to consider notional lateral loads. And a notional lateral load is to account for global geometric imperfections as well as inelasticity effects. How we apply this is it's going to be a lateral load with the magnitude of 0.005 times the factored gravity load. So we can almost use this picture over here that P is our factored gravity load. We'd multiply that by 0.005 and apply it to the top of these columns or at each story level, exactly how this force V is shown, this lateral load. Now, it's important that these notional lateral loads be applied independently in the 3D structure's orthogonal directions, and it should be done so in such a manner that we're getting the greatest destabilizing effect. So let's say we have lateral load for wind in the X direction. Well, it makes the most sense. Then we're going to apply these notional loads in the X direction as well for the greatest destabilizing effect. Wind in the Y, we'd apply a notional lateral load in the Y direction as well. Okay, so that's really just a quick overview of this simplified stability analysis method, but let us get into the new Annex O. And again, in particular, we're going to refer to stability effects and elastic analysis according to Clause O2. So there are a few different requirements here. Now, the first is geometric nonlinearity. And this is for second order effects that are required. The code in Annex O actually says, okay, we must consider big P delta effects, but here it also mentions P little delta effects. Now, there are conditions to neglect P little delta, and that is given in Clause O22, A through D. So if you meet one of these conditions, you don't necessarily need to consider those small deformations that are occurring along the member length. But we might be asking ourselves, what's the advantage then if I do include P little delta effects within my analysis? And what we get to do here is to actually set this U(1) factor equal to 1.0. And this U(1) is an amplification factor used in Clause 13.8 for member strength and stability design, and it's applied to the required moment force. And it's a factor to account for second order effects due to the deformation between the member ends. So it makes sense that if we can account for P little delta, then we're going to probably increase this factor so that we can consider in the design portion instead. Now, again, as I mentioned before, we saw this dialog box over on our right. Our method of analysis is a second order for load combinations that will consider both a big P delta and little P delta automatically. So we're going to meet these requirements set forth here within Annex O. So moving on to our second requirement, and this refers to geometric imperfections given in O.2.3. The code says that member and local geometric imperfections actually can be completely neglected for an elastic analysis. And what exactly is a local geometric imperfection? Well, I've went ahead and put a nice picture here of what exactly that might mean. Here is where we would actually deform the FE mesh along the member length to account for these uncertainties, these local geometric imperfections, maybe from manufacturing, for example. But the code tells us that we actually don't need to consider this, which is helpful because it can be pretty time consuming. What we do need to account for, though, is global geometric imperfections. And we have a couple of listed methods here that we can follow. Now, there are scenarios where we can ignore global imperfections, though. And this is for lateral load combinations. And if we meet the criteria listed here set forth by O.2.3.1. The first is that we have gravity loads primarily supported by vertical elements. And the second criteria is if the first to second order story drift ratio with reduced member stiffnesses, which we'll get into reduced member stiffnesses in just a minute, but if that ratio is less than 1.7 and we meet all of this criteria, then we can forget about global imperfections. Now, let's say that we don't necessarily meet this criteria and we actually do need to apply the global imperfections. Well, there are one of two methods given, again, within clause O2, and the first is direct modeling. This tells us that we must actually physically displace the member intersection points to account for these imperfections. And how we would physically displace them within the model, maybe we'd refer to clause 29.3, which gives a whole lot of information about erection tolerance values. It's also quite common to consider column out of plumbness of 1/500. So in addition to column out of plumbness, we might also be considering member out of straightness. And again, we're trying to consider the most destabilizing effect here. But this actually becomes very difficult. The reason why is because we're going to have so many different scenarios here of actually physically displacing these intersection points to consider that worst case scenario. So we're going to have multiple different models. Essentially, we're applying 4 different displacements in 4 different directions at each story level. So each member out of straightness effect needs to be considered with the relevant out of plumbness effect of the column. So this becomes pretty time consuming. So the more practical method might be method number 2 here for notional lateral loads. And this is given in clause O.2.3.3. So for this method, instead of directly modeling them, we can apply these notional lateral loads with a magnitude here of 0.002 times a factor gravity load. And we might be thinking to ourselves, well, I think we just covered notional lateral loads within the simplified stability method, and we did. But you'll notice that a big difference here between Annex O and the simplified method is the magnitude here applied for our notional lateral loads. We have a bigger magnitude of 0.005 here in front of the factor gravity load for the simplified stability analysis, as opposed to 0.002 in Annex O. And the reason for this is that the 0.005 from the simplified method is going to account for other effects such as inelasticity, whereas within Annex O, all we're accounting for here is global geometric imperfections, and that 0.002 comes from 1/500 for an imperfection value that we saw with column out of plumbness, for example. Now, once again, these should be applied in the direction for the greatest destabilizing effect. So we're talking about notional loads applied in the x direction with winds in the x direction, winds in the y with notional loads in the y, and so on. So over on the right-hand side, I have just a little dialog box, which we'll get into with our example today, of how we can take into consideration these notional loads within RFEM with what we call imperfections. And these imperfections allow us to not only consider this lateral load to cause member out of plumbness that we're seeing over here on the left, but we also can consider somewhat of a precamber or a member out of straightness if we wanted to as well. Now, the code does not address any member out of straightness, but just to let you know that is also possible within this dialog box as well. So While this is fresh in our mind, what we'd like to do then is to jump over to our RFEM example and to apply these notional or imperfections directly to the structure. So what I'm going to begin with here is to create a new load case. And the load case is going to be called imperfection in the X, with the action category here set to imperfection. I'm going to make a copy of this and we'll call this one imperfection Y, with again the action category set to imperfection. So I've created these two load cases, but similar to my loads above it, I need to also apply this directly to the structure itself. Well, I'm going to make sure that I have imperfections in the X selected here from my dropdown, and I go to Insert, Loads, Imperfections, Graphically. And this will bring up the same dialog box that we just saw within our PowerPoint. And from here, we can actually select the CSA standard, the 2019, that was recently added to this option. Now notice we have two different options here, the current loading or the gravity load combination. All this means is that under the current loading, we'll take the current applied axial load for each member and use that for the notional load. Now the alternative option is the gravity load combination, where the program will actually refer to a specific load combination that I select here within my dropdown for the applied gravity load. Now in our case, we're going to use the current loading, and notice that the program automatically refers here to the simplified method 8433 or Annex O233. Now our value set out in front here is 0.005. Remember, that's for the simplified method. If we're following the Annex O, we're going to change this to 0.002. And the picture explains quite clearly what's happening. I'm going to take this applied axial load in the member, Y sub I. I'm going to multiply it by this 0.002, and then we're going to take that value and apply it at the top of the member as a notional lateral load, N sub I here. Now keep in mind that we're going to apply an opposite and equal lateral load down at the bottom of the member, because we don't want to see higher reactions at the base of the member. We're only trying to affect the member along its length. I also touched on that pre-camber option. Again, the code does not address this, so this is set at 0, but you can set a member out of straightness here that's dependent on the member's axial force as well. So the final thing to do is to apply this imperfection related to the member's local Y or local Z axis. So for our imperfection in the X, I'm choosing my column's local Z axis. I click OK. And under my Views tab, before I apply this to each of my columns, I'm going to activate only my beam elements. So notice that my truss elements, my tension only, are completely grayed out. This way, I can take a look at an elevation view and I can apply that imperfection here to only my vertical columns. And now we have a nice symbol, and I'll turn this to wireframe view so it's a little bit easier to see. We see this imperfection with the magnitude 0.002 that will be taken into consideration for these members according to the global x-axis. Now for imperfections in the Y, or notional loads in the Y, exact same process. Under Insert, Loads, we go to Imperfections. Graphically, nothing changes here. The only thing we're going to do is apply this to the local Y axes instead. And by the way, if you need to quickly orient the imperfection or the notional load in the opposite direction, just add a negative here in front of this coefficient. So for imperfections in the Y, we're going to apply these according to the local Y axes of the members. I click OK. And then once again, I'm going to select all of my column elements here. So you'll notice that this imperfection is now according to the global Y axes. So we have efficiently applied these imperfections here to the structure, but now we need to combine them with our other load cases within our load combinations. So I can do that by jumping to my load cases and combinations, and under my combination expressions, which you remember we've already visited this tab, there's the option here to apply the imperfections that we just created to these load combination expressions. So when I check this checkbox, you'll notice that automatically this dialog box is brought up and it says, okay, we notice that you have two imperfection load cases that you created, imperfection in the X and imperfection in the Y. Do you want to use both of them for our factored load combinations? Yes, we'd like to use both of them. I'm going to take this one step further to activate this option down here, subject to a specific load case. Now, remember, we're always creating the greatest destabilizing effect. So imperfections in the X should be applied with wind loads in the X. I never want the imperfection in the X to be applied with wind loads in the Y. It makes no sense. It's not the worst case scenario. All we're doing is creating additional load combinations that really aren't useful for us. So we can kind of filter those out by selecting this option to tell the program never to use my notional load in the X with winds in the Y. So LC5 will never be used with LC4. In a similar manner, my imperfection in the Y, I'm going to select the option here to never use this imperfection with load combinations that have wind in the X. And I click OK. So this will be taken into consideration. We'll see in just a minute under our load combinations tab. The other thing I want to do is to activate this option here differently for each combination expression. The reason why is under serviceability, I'm going to leave this unchecked. I don't want any imperfections or notional loads applied to my serviceability load combinations I'm using for deflection or drift calculations. Well, under the load combinations, you'll notice that this list looks quite a bit longer. So we want to ensure that these notional loads were accurately applied to these load combinations. So if we take a look at a gravity-only load combination, so 1.4 dead. Well, I take a look at the load combination right below it, and now I'm seeing 1.4 dead plus imperfection in the X. Then I also have a third load combination here, that's 1.4 dead plus the imperfection in the Y. So we're going to consider all those scenarios for this gravity load combination. But if we jump down here to one of our load combinations with an applied lateral load, such as wind in the X. So for this load combination 7, we see dead plus snow plus wind in the X. Well, load combination 8 is dead, snow, wind in the X plus imperfection in the X. We will not see wind in the X with an imperfection in the Y. Again, it doesn't make any sense. This isn't the worst case scenario, so we don't need to have additional load combinations here. We take a look at our next load combination. We have dead snow, wind in the Y, and then we have dead snow, wind in the Y with our imperfection in the Y. Now, sure enough, with our serviceability or unfactored load combinations, no imperfections are considered at all. So this is exactly the scenario that we wanted. We've accurately applied those notional loads to the structure. Okay, so we also can view here graphically those imperfections, the snow load, wind loads, everything applied to the structure at once if we're interested in seeing this graphically all together. So now that we have applied our notional lateral loads, let us go back to the PowerPoint here to discuss the last requirement according to clause O.2.4. And this is reduce member stiffnesses. Now, we reduce the member stiffnesses when we are applying stability according to this method here with an annex O. And we want to account for the initial geometric imperfections, the inelasticity and uncertainty in stiffness and in strength. So what we'll actually find is that there are a lot of similarities here with these requirements to the direct analysis method given in the AISC Chapter 7. But there's also some big differences as well. So the CSA states that we must reduce the member's axial stiffness, so that's EA, and the flexural stiffness, EI, by a couple of factors. And the first is a 0.8 reduction factor, so that's pretty easy. But we must also consider a tau sub B factor, and this is actually dependent on the factored axial force, C sub F, and the axial strength of the member, C sub Y. And we use these equations shown here in the lower right direction directly from the CSA standard to calculate tau sub B. So we can see the higher that ratio is, the smaller that tau sub B factor is going to reduce our stiffness. But for pretty high ratios, tau sub B is just going to be equal to 1.0. Then we apply both of these factors here to EA and EI of the member. Now, a big difference when we compare to the AISC direct analysis method is that tau sub B and 0.8 are certainly applied to the flexural stiffness, but we are not going to see that tau sub B applied to the axial stiffness within the member. So that's a pretty big difference. Now, it is recommended to apply the stiffness reduction to all members that contribute to the lateral stability of the structure. However, the code goes on to say that in order to avoid localized distortions, it's really recommended to apply to all members. And that's what we'll be doing in our example today, is applying this stiffness reduction to every single member within our example. Now, we should also consider applying the stiffness reductions to the shear stiffness, GA, and the torsional stiffness, GJ, when the stiffnesses contribute significantly to the lateral stability. And this is a big difference here between the AISC and the CSA standard. So what we potentially have the ability to do is to also consider this 0.8 and tau sub B reduction factor for the rest of the stiffnesses as well for the member, not just axial and flexural. And over on the right, we have our dialog box where in just a minute, we'll show how to apply these stiffness reductions. And you can see that for the CSA standard, we actually list all the different stiffness options here and how those factors can be applied to them differently. Now, it must be noted that the stiffness reduction should not be applied when we're considering drift, deflections, vibrations, periods, and so on. So what this means for us today is that for our serviceability load combinations, we should be considering the full stiffness of the member rather than reducing the member stiffness according to O.2 here. So once again, let us go back to our structure and we will apply these stiffness reductions to the example today. So as I mentioned, we're going to take the code's recommendation and select every single member here within our model. And then if we just simply double click on any one of those members, we have this modify stiffness tab. And by default, the definition type is set to none, just meaning we're not going to apply any stiffness modifications to the structure. What we're going to do is to select the CSA standard S16 2019 that was recently added. And this is referencing again clause O.2. So notice tau sub B is listed here and the default is set to iterative. All this means is it's going to refer back to the standard for those formulas to take into consideration the axial force to axial strength ratio and to calculate what tau sub B should be. Then we also have our 0.8 factor, and that's just listed in this first set here. Notice that the flexural stiffness and axial stiffness are grayed out. That is because this is a code requirement. So when you choose the CSA standard, we're automatically going to assume that you will be applying the stiffness reduction to flexural and axial stiffness. But we do give you the option here, which the default is unchecked, to check the stiffness reductions, both tau sub B plus the 0.8 factor to the torsional stiffness, as well as the shear stiffness. So if that's an approach you want to take, you can manually turn on those checkboxes here. Now for today, we'll just be applying this to the flexural stiffness and axial stiffness. I click OK, and now automatically every single member within this example will have a stiffness reduction applied. But keep in mind that we said for our serviceability load combinations, I actually want to consider the full member stiffness. So how can we do that? Well, remember under the calculation parameters where we set the second order analysis for all these different load combinations, you'll notice by default that it is automatically activated. The program will consider these stiffness reductions, whatever we set in that dialog box we were just looking at for members automatically. So it's automatically going to consider the stiffness reductions for every single load combination here. All this means is that we can jump down to our serviceability load combinations. We can highlight both of them with our shift key, and we just simply turn this off. So now the full stiffness of the member will be used for only these two serviceability load combinations, but we jump back to our ultimate limit state load combinations, and this option is checked again. So that's how we can easily consider full stiffness versus the stiffness reductions for different load combination considerations. Okay, so we have finally applied all of these different requirements to our model based on the new stability within Annex O. We're finally ready to run our calculation. So I go to calculate all, and the program's just cycling through my load cases, my load combinations, taking into account stiffness reductions, notional loads, second order analysis, and eventually we're presented here with our results. So as I mentioned, we will be seeing our results available to us in the lower right-hand corner here within the project navigator. And I actually am looking at the global deformations here, and I can select any one of my load combinations just to cycle through these. And I think deformation is important just to get an understanding if we properly modeled everything, the loading is correct, so that we're not seeing extremely high deformations, we're not seeing anything fly off the page, and everything looks well modeled here for this scenario. But we know for steel member design, what we're most interested in here is the member internal forces. So what I can do is to activate my member internal forces within my project navigator. And for the sake of simplicity here, let me just select one of these moment frames, and I will select the visibility by the selected object here. Can zoom in. So I'm currently viewing the member axial forces along the full member length here for this frame. We also can activate shear forces in the weak axis direction, the strong axis direction. We can take a look at bending moments, for example, in both the strong and the weak axis direction. Now, for any one of these members, we also have the ability here to right-click on the member and view the results diagram. So this results diagram just allows me to turn on and off these internal forces or deformations, and we can see in a bit more detail what's going on along the member length. We can even cycle through to these different load combinations here at the top. Now we have the ability to average out regions, to smooth regions. We can export this information to Microsoft Excel. We can add it to our printout report. So quite a bit of information here. Now, everything has been shown to us graphically so far with our member results, but we also can view the internal forces within table format. So if I go ahead and increase my table down here at the bottom, and I want to take a look at table 4 for my results. And down at the bottom, we have these different tabs here. What's also nice is I can right click on any one of these tabs to just see a quick list of all the tabs available to me. Now notice a lot of these are grayed out because they're relevant to surfaces, which we only have members for today's example. But I can jump to my members' internal forces. And when I'm within this dialog box, you'll see that everything is synced up in the background. And I'm currently viewing my max forces for the load combination selected here, such as my axial forces, my shear, bending moment, and so on. And that big red arrow is showing me exactly where the controlling internal force is for that particular member. Now, in turn, I only have this frame activated graphically, so I can also select any one of these members and the table will jump to that particular member. And then we can take a look at here any of the information in a bit more detail. Now, the member internal forces are what we're going to want to use for our design purposes according to the CSA standards. So we have the ability here at the click of a button to export all of this information directly to Microsoft Excel. So let's say we have our own in-house tools, we have Excel spreadsheets, or we'd like to do the design outside of RFEM. That's certainly possible, and this is a helpful feature that will allow you to export all of the needed information. But for us today, I'd like to make the clear distinction that we'd want to utilize the add-on module RF-STEEL CSA for our member design. So what we're going to do to access this add-on module, which is still integrated within RFEM, is to jump here to our list of add-on modules within the project navigator. And you can see that we can always right-click on a module, select it as our favorite to jump it up to the top of the list. This is a little bit too overwhelming because clearly there are a lot of add-on modules. We can always access any of the add-on modules which are categorized according to their material within this drop-down option. So we'll choose Design for Steel, and we will launch the Steel CSA add-on module. Now, this is just a dialog box that pops up within the main program RFEM here. I don't need to worry about inputting in materials, cross-sections, loading, load combinations. Everything is brought in from that main program. What I am specifying here is information that is specific to the CSA standard for the design purposes. So we're talking about effective length factors, unbraced lengths, and we'll see all of that as we move through the example today. Now, the first option that we want to select is over here on the right. Notice we have the 09, the 14, and now we have the 2019. Then we want to select the members we'd like to design. So if you're not necessarily interested in designing all members at once, what we can do here is to select, let's say we want to choose just our columns. Well, once again, I'm going to go under my Views tab, and I will select just my members by type beam. Then you'll notice my truss and my tension only members are deselected, so I can easily select those column elements here, and I click OK. You'll also recall those sets of members that I created for those main rafter elements here, because I said, hey, it doesn't impact the analysis, but once we get into design, I want to consider these as one continuous member. I don't want to design these individual segments. So that's why we have the ability here to design what's called a set of members. So for this, I do want to show you one set of member design because it does differ from just a typical member element. So we'll select set of members number 2 here, and I click OK. Then for the ultimate limit state, I'm going to select all of my factor load combinations and move them over to the right-hand side. Serviceability, I'm going to choose my unfactored load combination. So this is going to be for my deflection checks that we can do directly within this model. Once I move these load combinations over here to the right-hand side, I get an additional table down here at the bottom for serviceability data. So we'll eventually get there in just a minute. But now that we have input this information under the general data, what we're going to do is just to simply move down our list here. So we're going to take a look at our materials. Again, brought in from RFEM, 350W, material properties are shown here. Cross sections, same concept. We have our W310 by 79, and I can select that here. The program highlights which members are being applied, and I have my W130 by 24. Now, the other members are grayed out here because I have not selected them for design within this add-on module. The section properties are given to me again down here at the bottom. The intermediate lateral restraint. So this is if we had top and bottom flange bracing along the member length, and this is going to impact our lateral torsional buckling, stability design. So for any one of these members, which again, everything's synced up here in the background, I can choose member number 1, member number 6. If we had any top or bottom flange bracing, I could input the number of restraints as well as the increment that they're placed at along the member. We don't have that scenario today, so we'll leave these unchecked. Now we're moving on to effective lengths for members, and we also have effective lengths for sets of members under a separate table. So let us begin with our columns or our members here. And this is all stability considerations. So we have buckling about the strong axis, we have buckling about the weak axis, torsional buckling, and lateral torsional buckling. Now, if we're thinking for any one of these members, let's just say we have some sheathing or whatever it may be that are bracing any one of these members in these directions, and we're not concerned with buckling, let's say weak axis buckling, all we need to do is just to uncheck this option here, and the program will not consider it within the design. Within each one of these sections, we have the effective length factor. Notice the default here is set at 1.0. You can either make that change in the cell format up here at the top or within table format down here at the bottom. And if we click on this three little buttons, what's nice is that we get a separate dialog box that pops up here. If we decide, okay, I don't want a pin condition, but let's say I have a pin fix condition or whatever it may be, there's the nice table format here for either the theoretical or the recommended values that we can set quickly for strong, weak, and torsional buckling considerations. So we'll leave this as 1.0 for all of our members today. Now, the second column listed here is going to be the unbraced length. And we all know how important unbraced lengths are. By default, the program will set this to the full member length that it knows within RFEM. But if we have any connection points, any other members that are framing in, bracing this particular member at something less than the full member length, then we would definitely want to input that length here. This drastically affects our capacity for stability consideration. So we'll want to adjust that if it's something other than the full member length. And we'll do so within our sets of members in just a minute. But for our columns, we're leaving everything at the full member length here. So as I mentioned, we also have this effective lengths for our sets of members. Remember, this is our rafter up here at the top. So why do we have a different table? Well, the concept is pretty similar. We have buckling about the strong axis, weak axis, torsional buckling, lateral torsional buckling. But here's the difference. I'm going to jump down to the nodal supports, and this nodal supports is only available to me when I am designing sets of members. And the code, any code really for this matter, does not really address these continuous members that are not in a straight line. So this is kind of the advantage of creating the sets of members, that it does need to be in one plane, but it doesn't necessarily need to be in a straight line, which is exactly what we have here. But how do we design stability, for example, lateral torsional buckling, when the code doesn't address a situation like this? So what we do is to take a more theoretical approach. And we're going to take this sets of members and we're going to completely extract it away from the rest of the structure. So all we're left with is this set of members just kind of by itself here. Well, if the program doesn't know how it's framing into the rest of the structure, what we additionally need to do is to set nodal supports along the member length. And what we're going to do once we set these nodal supports is run an eigenvalue analysis. And this eigenvalue analysis will give us a buckling mode shape and a critical moment here that we can use for the resistance. And that's what we'll be using to compare for our stability calculations. But again, we need to pay careful attention to these separate eigenvalue analysis, and in particular, these nodal supports. So if I take a look at along the member length, the program is automatically assumed for my set of members number 2 that I have a nodal support at both ends. So node number 14 and node number 9. If I zoom in here, I can see that node applied here. And for each of these nodes, we have 4 degrees of freedom. We're going to assume, and currently we're looking at this node up here in the upper left-hand corner, that this member is going to be braced in and out of plane in the weak axis direction. I'd say that would definitely be the case here with those truss members framing in. We're also going to restrain the member so it's not free to rotate about its own axes with torsion. I'd also believe that to be the case. I'd also say, though, that we're going to restrain here the member about the Z prime axis, so this vertical axis. Because we have these columns framing up on either end, it's not going to have the ability to rotate about the global Z axis either. Then we have one more degree of freedom here for warping. So if we had any warping constraint, we could take that into consideration by checking this option. With warping, we have another special detail settings here, and this allows you to set the type of warp stiffening. So if it's not fully fixed or not fully released, but we have some type of spring, what we can do here is to select one of these options, such as an end plate, a channel section, an angle. Let's say we have an angle here that's resisting or helping to resist warping. Well, we could set the material of that single angle. We would set the dimensions of that single angle. So just making up some numbers here of a 4-inch width, thickness of 0.25 inches. And let's say the height or the depth of our beam today is 12 inches. The thickness here is going to be 0.3. Notice that the program automatically calculates this warping spring for us. So all we need to do is to hit OK, and that spring stiffness is imported back into this table. So that can be really effective if you have some type of spring option here. Now we don't have any warping restraints, so we'll just leave this as unchecked for today. Now, of course, we have these nodal supports at the member start and the member end, but remember, we also have these truss elements framing into the weak axis direction along the member length that we want to consider, because that's obviously going to give us quite a bit more capacity when it comes to something like lateral torsional buckling. So what I do here is just to graphically select node number 10, we'll graphically select 11, and finally we select node number 12. I'm assuming for each one of these additional nodal supports where these truss elements are framing in, that we are going to restrain the member in the weak axis direction, so in and out of the plane. We're not going to allow rotation, so it won't be able to rotate freely about its own axis, but I'm going to leave the restraint about the Z prime axis unchecked as well as warping. We also can get pretty technical here. If we wanted to slightly adjust the angle of this rotation to get more precise, we definitely could do that, especially since this is at an angle here. We can add in an eccentricity. So all of this is possible. Now, if we jump back to the sets of members, what I want to point out is you'll notice that the program doesn't default here to the full member length anymore. It refers back to those nodal supports that we just set, and it's going to adjust the unbraced length in the weak axis direction to now 10.11 feet, which is the distance between those nodal supports or between those truss elements. Same thing for torsional buckling, 10.11, and then lateral torsional buckling, everything's controlled underneath the hood with that eigenvalue analysis, so we don't worry about anything there. Now, when we look at strong axis buckling, you can see that the length is the full 40.45 feet. And I would say that this is correct. We have no element supporting this structure underneath it, no columns framing up that are going to brace that member in the strong axis bending direction. So we'll leave this as the full 40.45 feet. Now, this additional table here, member hinges, this is just if we had any member hinges along the set of members. So I could graphically select a member and I could apply a shear release, moment release, or warping release. Again, this will affect that eigenvalue analysis, but we don't have that scenario, so we can leave this as empty. Finally, we have serviceability data. So this is for our deflection checks. Now, our serviceability load combinations are really only gravity load combinations, so I'm probably not so interested in checking necessarily my deflections for my columns, but rather I'm going to just check the deflections for the sets of members. Now I can just type in 2 here, or I could graphically select it. The full member length will be used at 40.45. The pre-camber can be set here if we had one, and then we'd also specify as a beam or a cantilever. So we might be wondering to ourselves, well, where is the limiting deflection ratio set then? And that's actually controlled under the details tab here. If we pull up in the details tab at the bottom, here's where we can set our limiting deflection ratios. L over 360 for simply supported, L over 180 for cantilever. So this is what we'll be comparing our deflections back in the RFEM analysis to once we run our design. Just a couple other things to touch on within this dialog box. You'll notice that we have our slenderness ratios that are set here. This is according to clause 10.4.2. This is according to the code, but there are a couple exceptions, such as for tension cords and top cords, where maybe we need to make an adjustment. So we allow you to do so here. One really important topic is this structure type here. And if you remember way back when, we talked about this use of one factor in the PowerPoint, and we related it to P little delta effects. Now remember, this use of one factor comes from section 13.8, and it's to account for second order effects between the member end. And if we are running an analysis that considers P little delta directly within the analysis, we have the advantage here to set this equal to 1.0. Now, within RFEM, when we run a second order analysis, we are considering P little delta. We are designing according to the stability considerations for an elastic analysis within Annex O2. Therefore, I can leave this option checked on to maybe get a little bit more capacity out of the member. There are also some other requirements within the code that if we're using the simplified stability method, forget Annex O, you also can set this use of 1 factor equal to 1.0 for unbraced frames, again, according to clause 13.8. So just something to keep in mind. But remember, we are taking into consideration P little delta. We are designing according to Annex O2 stability requirements, so we can leave this option checked. So once we have defined all of this input information, we're finally ready to run our calculation. It solves within a quick second. And what you'll notice here is that we're getting the design results. We're just bringing in the internal forces from the RFEM analysis, applying the CSA equations to give us our design ratio. We can view design by load case. We can view design by cross-section, sets of members, and members. Now for our table here, everything again is synced up in the background so that as I'm scrolling through this table, that big red arrow is going to show me exactly where that controlling internal force is for that particular check, as well as which member I'm looking at. So you can imagine with hundreds of members, it's really helpful to see exactly which member you're looking at in comparison to the table. So for each one of these members, you'll see here that we're actually giving you a code check for every relevant section within the CSA. This includes axial compression, bending about the y-axis, the z-axis, shear, stability, and so on. And for each one of these particular results, we can expand on our table down here to view the design internal forces. We can see how the cross-section was classified. And then finally, we get our design ratio. All of the variables are listed here, along with all of the code references directly. So we're trying to give you as much information as possible rather than being a black box program and just spitting out a number and saying it's passing or failing. But you can actually trace back to where all these variables and equations are coming from to ensure that your calculations, maybe you're doing them by hand, match the programs. Now, we might be thinking, well, this is pretty overwhelming here. What if I'm just interested to see the controlling check for each member rather than every single check within each one of these selections here? Well, we can use our filter options here to choose only the max. We hit the filter, and now we're seeing only the max design ratio for each one of these members. Now, all of this information, similar to what we've seen in other portions of the program, can be exported right here to Microsoft Excel. So if we'd like to do some further sorting of this information, we could do so. I do want to jump back up quickly to my sets of members, because you remember this one was a little bit special when it comes to our stability check. And if we scroll down here, we're going to see that elastic critical moment for lateral torsional buckling MCR provided. And this is the value that was determined from providing that or analyzing this separate sets of members with the eigenvalue analysis. So we're extracting it away from the rest of the structure to come up eventually with this critical moment that we'll use for the design ratio. Even more so, we can take a look at this buckling mode shape. So what's happening here is this is the member right before failure where we could calculate that elastic critical moment that we're using for the design purposes. So we're kind of viewing according to those nodal supports that we said exactly how the member will fail here. So again, a little bit special with those sets of members. Also remember too, we check serviceability for this sets of members. So we can view here the deflection, the total deflection, as well as the limiting deflection based on that L/360 ratio for our design ratio 0.46. If I scroll this down, sure enough, that big red arrow is pointing to where my controlling deflection is, which is where we'd expect at the midspan of this unsupported along its length for that sets of members. So all of this information is available in table format. Of course, we can view this graphically as well. So we're technically still within this RF-CSA add-on module. We're just viewing our results graphically within RFEM. And here we can activate the ultimate limit state design. We can see our design ratios along each one of the members. We also can view here serviceability limit state as well. So if we're interested in seeing those deflection ratios for our sets of members, because those are the only ones that we had considered, we can view them graphically here. The final thing I want to mention before wrapping up our webinar today is just optimization. This is a common question. Can we optimize? Yes, if you jump back to this cross sections table here, you'll see the optimize column where you can actually set this to a few different options. When we set this to the current row, it will consider all W sections from the CSA standard, or we can create what's called a favorites list within our cross section database where maybe we select only a few W shapes to be chosen for the optimization process. So once we do that, we can rerun the calculation. The program will come up with, okay, we think approximately this member will work. Well, then we would export that member back out to RFEM to replace the original member with the true member stiffness, rerun the calculation, and then we'll rerun the design here. So that can just be a workflow process that you can follow for optimization as well. All right, so we will go back to the PowerPoint here just to summarize our presentation today. So you can always visit our website at deluwell.com to learn more about RFEM and the RF-STEEL CSA add-on module. This presentation will also be recorded, so you can find that recording on our website where you actually registered for this webinar or our YouTube channel. You can even download this example model that I used today, and if you'd like, you can open it within the free 90-day trial version. So the trial version is full capability, includes all these add-on modules. You can open up this example today to just do some investigation yourself. Quite a bit more information as well on our website. I do want to mention we do have a dynamics training coming up on Tuesday, March 23rd. So feel free to sign up for that. It's a 3-hour training specific to dynamic analysis within RFEM. If you have any questions or comments about today's presentation or any of our products, feel free to either send us an email in our Philadelphia office, and that's info@deluwell.com, shown here at the bottom, or you can give us a call at 267-702-2815. We will have many more upcoming webinars, approximately once a month. You can register at deluwell.com under support and learning and webinars. As most of you know, I tend to send out a reminder email about a week before these will take place, so feel free to keep an eye out for those and to sign up directly through the email notification. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So it is a requirement from the states that we are pre-approved providers that attendees be here for the full 60 minutes in order to receive that PDH, and will automatically be sent out. It's not right after the webinar, but it'll usually be within the next day or two. So keep an eye out for that directly to the email address that we have on file for you. If you yourself did not register for this webinar with your own name and your own email address, but let's say you watched with a handful of colleagues, you will need to request that PDH at info-us@deluwell.com. So again, if you did not register as an individual for this webinar and you were here for the full 60 minutes, please request that PDH. Let us know who you watched it with the email address info-us@deluwell.com. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at the next presentation. Thank you.